Welcome everyone. So today we're very happy to have Mirjam Cvetic visiting from UPenn, who will tell us about higher symmetries, Eta Invariants, and how these relate to anomalies. Thank you, Mirjam.
Hey. Well, thank you, Max, and also to Dan, who unfortunately couldn't be here, and others for the invitation. It's actually the first time that I'm talking to the group of more math-oriented people, though I have to admit I myself am not that math core in my training. So what I want to do in this talk is actually giving you an overview of a program that we have primarily pursued at Penn by studying the origin of higher symmetries in non-perturbative quantum field theories and studying more refined data about anomaly coefficients in such theories that will be quantified in terms of so-called Eta invariances. This approach will be primarily via constructing of such theories and studying these features within geometrical engineering. So the core of this talk is based on the recent paper with Ron Donaghy, mathematician at Penn, Jonathan Heckman, colleague at Penn, and Max Hübner, extensive collaborator and here at Harvard. A lot of background, but also the ideas that lead to results in this most recent paper are based on a programmatic work that we have also pursuing at Penn, the more recent one with Ethan Torres, and earlier on just together with Jonathan, Max, and Ethan. So to motivate this study, we attempt to address the features of higher symmetry structures in quantum field theory by employing the so-called techniques of geometric engineering. That basically leads us to string theory or M theory, where we put extra dimensions on non-compact spaces and then describe in terms of geometry of these non-compact spaces the quantum field theory features in the resulting quantum field theory. So generically, in order to deduce features of quantum field theories, these non-compact spaces are, in general, singular spaces. So the typical approach within this framework is to take the singular geometry of extra-dimensional space and resolve it, at least locally, to smooth spaces. And then further employing techniques particularly of algebraic geometry or topology to reach technical results in quantum field theory with great computational success. And that was, and still continues to be, a broad program pursued by many different groups around the world, of course also including that at Penn. However, when we are studying features, in particular this higher symmetry structure in quantum field theory, those quantities that we want to deduce about quantum field theory are often topological in nature. So because they are topological, not even algebraic, it is expected generically that calculations for these quantities should be able to address directly in singular spaces. And so in particular, with some techniques in algebraic and or differential topology. Well, a situation may be even more difficult in general. We may be dealing with singular spaces which are so complex due to its complexity of those spaces, we may not be able to resolve them. And we may have to, basically being stuck, we are stuck with singular geometry. So the message of this program that we are pursuing is to trying to address the features of higher symmetry structures in quantum field theories by hopefully directly working in singular spaces.
So the singular spaces are here either Calabi-Yau or G2 or things like that, right? Or
Yes. I will. In general, we would like to talk about quantum field theory, resulting quantum field theories with supersymmetry, because we may have overall more control over the effective results, right, of the effective theory and so on. And in this case, the spaces would have to have special holonomy.
But the big selling point is, as in the last bullet point.
Yeah.
But since a priori it can be anything.
That's
Yes,
yeah,
and
so-
actually calculations
So
are
symmetries are topological, do not need special anomaly in principle,
right.
but it helps.
So the aim is, yeah. So in any case, let me just point out some recent examples where novel results were obtained directly in singular geometry about resulting quantum field theories. And so the example of such geometries will be related, will be described as so-called nested, non-isolated singularities. Not just the particular highest codimension singularity, but interplay of different codimension singularities. And so I would like to refer to that, to non-isolated singularities. And of course, the resulting quantum field theories are more complex there, and important results have been actually achieved by different groups, but I should especially highlight the program that we have pursued at Penn. Another example would be example of so-called frozen singularities, where one could also address some of these features directly in this specific single geometries that we actually cannot resolve even. And some initial progress along this direction in more recent years was also pursued by people that were at some point associated with Penn. And as I'm hearing from Max, it continues to be advanced further, also by the subset of people here. Well, another example in particular in the context of so-called F theory were examples of terminal singularities, and again, there was some novel results in those directions that were in recent years initiated by Weigand and collaborators. And bringing it to your point, okay, there is progress also in directly studying singular geometry that results in non-supersymmetric quantum field theories. Okay, and again, collaborators at Penn, in particular, Max and others advanced some of the studies in those directions. Okay, so the focus here in this talk will be really highlighting new results in singular geometries with so-called nested, non-isolated singularities. So the rest of my talk will be a little bit of an fast overview, or I would say highlights, associated with introduction of higher symmetry defects and operators, the way we study them within geometric engineering. As a next step, we'll address the resulting features of symmetry field theories in this context, both for isolated and so-called nested symmetry field theories, which are associated with non-isolated singularities themselves. And then the more refined study of the anomaly coefficients in resulting TFT in this more general context, both isolated and non-isolated singularities directly in singular geometry. Okay. saying, and maybe some concluding remarks at the end. So I could choose different dimensions, different string theories. So I'm going to choose one particular prototype. Okay. So the prototype that I'm going to focus on would be M theory on non-compact Calabi-Yau threefolds. And it will be conical. Threefold, so it's a cone. Again, examples on which the results will be given will focus again on prototypes of orbifolds, where we have the non-compact, three complex dimensional space, and we mod up by a finite subgroup of SU3 holonomy. So the resulting quantum field theory that we are studying would be from 11 minus 6, 5-dimensional quantum field theory, and because of special holonomy, it will be supersymmetric quantum field theory in 5 dimensions. And with this focus, trying to highlight results here. Of course, one can study different examples on 2-folds, 4-folds. One could choose type 2 string theory, and so on. There are lots of things and are studied in papers, but this is the prototype that I'm going to single out to demonstrate some of these results. Okay? So you probably have seen that, and this is just pictorial thing that highlights the essence of higher global symmetries in quantum field theory, introduced about 10 plus years ago, which involves the introduction of extended defects in quantum field theory and asymmetry operators that act on these non-dynamic defects. The prototype example in this context would be one-form symmetry, which is generated by string type, Wilson line type defect, and a symmetry operator that is also closed loop, typically that acts on this string defect, and it's a symmetry operator. We also, of course, are also typically dealing with the standard zero-form symmetry generating by the point defect and a symmetry operator acting on it, typically H transformation operation. There are examples of more involved quantum field theory when we are dealing with the intertwining of one-form symmetry with zero-form symmetry themselves, and they together form a bigger intertwined structure that leads to so-called two-group symmetry. And it will be that part that I want to focus on in quantum field theory. In geometric engineering, the way it will arise from extra dimensions with non-isolated singularities. Okay. So primarily, I want to focus on these aspects. Anyway, now to address higher symmetry structure in geometric engineering is extremely natural, I would say, because the origin of these higher symmetries becomes very geometric. What we are dealing with here is we have resulting space-time with quantum field theory, and we have extra dimensions that we put on particular conical non-compact space. So for us, that would be Calabi-Yau singular threefold. Okay. So the way the higher symmetry defects appear, they will appear as branes, resulting in some, for one-form symmetry, in a Wilson type line in resulting quantum field theory, but in the extra dimensions, they will be associated with the branes wrapping non-compact cycles that extend typically all the way to the boundary Symmetry operators, on the other hand, will be associated again with branes, but so they will act as operators acting on the defect in the resulting quantum field theory. And in the extra dimensions, they will be associated now with these branes wrapping cycles that sit on the boundary. And they wrap, this extended defect there just on the boundary. So these features of such a defect group associated with the brane wrapping non-compact cycles can be quantified in terms of relative homologies. So the defect group in M theory, that will be our focus, will be associated with M2 branes. That will give us defect groups specified by relative homologies. And will result in the electric part of the defect group. So magnetic part will be associated with M5 branes wrapping non-compact cycles quantified in terms of this relative homologies, and will specify the magnetic defect group. So similarly, the symmetry operator typically will be now associated with the corresponding homologies that live only on the boundary. Okay. So for the rest of my talk, I will focus primarily on the electric defects that will be associated with M2 branes, and they will be associated with Wilson lines, and so they will be symmetry groups of the defect of one-form symmetry. That will be the primary focus. One could generalize all that to other examples as well. Okay? All right. Now, let me turn back to the quantum field theory aspects of studying higher symmetry structures. So on the quantum field theories side, we would like to understand further how such higher symmetry structures are represented in the resulting quantum field theories. Are they broken? Are they not? Okay. And also possibly to address how the symmetries further constrain the representations. And most importantly, since they are topological in nature, the associated anomalies of them. Okay. So to address such specific symmetry structures, one can always isolate these structures in the so-called topological field theory that is one dimension higher than the original quantum field theory. And this was maybe unfortunately named symmetry topological field theory, SIM-TFTs, okay, where in this extra dimension, we start originally with d-dimensional quantum field theories with the physical spectrum properties of it, okay? And now we extend this theory into SIM-TFT in one dimension higher, where on one side, here, we are dealing with the physical boundary conditions of the physical degrees of freedom of original quantum field theory. And on the other side, we are dealing with boundaries conditions which are typical topological in nature. Okay. And so sometimes many symmetry structures will depend only on this boundary condition on the other side of this one-dimension extended SIM-TFT. Okay. Well, SIM-TFTs are again natural in geometric engineering. So this prototype that we are dealing with, okay, first let me focus on example of isolated singularities. So the extra dimensions are associated with the conical non-compact geometry. And we have a singularity at the tip of the cone. It's this singularity at the tip of the cone that quantifies, in resulting quantum field theory, the physical quantum field theory degrees of freedom. For example, the gauge group, the spectrum, and so on. Okay? Now, if we compactify this extra conical geometry along this radial slice over the boundary, we end up with an extra dimension, naturally, which is the extra direction associated with sim TFT. So at the tip of this cone, where the isolated singularity sits, we are dealing with physical degrees of freedom that appear there, boundary conditions associated with that side. And on the other side of the slice, namely the actual boundary, we are dealing with topological degrees, boundary conditions themselves. So the way we deduce these boundary conditions, actually, because this is now M theory put on the space and then compactifying this boundary over radius slices produces for us, okay, the boundary conditions that we could derive from the resulting effective supergravity theory that was there in 11 dimensions. And again, over last few years, that was an extensive program pursued by a number of groups. Okay, now let's generalize the SIM-TFTs. So going back to quantum field theory itself to begin with, okay? So how we would like to typically represent more general SIM-TFTs, namely the so-called nested SIM-TFTs, the way we named them in this paper from about a good year ago. Okay. The prototype of such generalized nested SIM-TFTs in quantum field theory would be to consider higher dimensional quantum field theory and insert into this higher dimensional quantum field theory a defect quantum field theory in lower dimension. So the way we would see that is, here we start with this resulting quantum field theory, and inside we have a lower dimensional quantum field theory viewed as a defect inside bigger quantum field theory. Now we can build the corresponding nested SIM-TFT from this perspective on. So for most relevant features of resulting SIM-TFT, we would not need all the capital D dimensions of the bigger quantum field theory. So we can curl up, Kaluza-Klein reduce it to just one dimension higher quantum field theory than this defect quantum field theory. It's sufficient for most of the purposes where we want to study features of SIM-TFT. So we can, this KK reduced bigger quantum field theory here is now just in one dimension bigger than the defect quantum field theory. It's sufficient. So this is where we are dealing now with the quantum field theory along this line of bigger, so with the bigger one. And now the defect quantum field theory is just now, of course, the point, or view it as a corner, at the edge of this bigger quantum field theory. Now, above the bigger quantum field theory, we build SIM-TFT, which is now in D+2, which is in one dimension higher, right? And I would call this often bulk SIM-TFT, right, beyond the big one. above the corner defect field theory, we also build SymTFT, which I would refer to as edge boundary SymTFT. Okay? And there are boundary conditions that are now imposed also from the bulk to boundary SymTFT in this more complex system of quantum field theories. So the resulting SymTFT is now of a more complex nature, namely nested nature. And so this is one concrete realization, right, or interpretation of nested SymTFT the way we would view it directly in quantum field theory. Prototype, okay? Well, in geometric engineering, nested SymTFTs are also very natural, okay? So we will see that these nested SymTFTs are associated with now non-isolated nested singularities in the extra dimension. Okay? So what SymTFT is to isolated singularities, nested SymTFT is to non-isolated singularities. Would like to argue. Okay? And this observation and concrete examples worked out in this paper were very shortly afterwards generalized and expanded also in other works. So the notion of this nested SymTFTs via geometric engineering has become again a big program in studies of higher symmetry structures here. Okay, so let me discuss a conical prototype of non-isolated singularities and construct from this prototype a nested SymTFT itself. So the prototype will be again an orbifold, so Calabi-Yau threefold, okay? But in addition to codimension 6 singularities, we would be dealing with the sectors where we have codimension 4 singularities, which we like to refer to as flavor brane singularities, okay? That are codimension 4 loci and will be typically associated, again, with some cones, in this case of S3 over some fixed action group. So let me show you the prototype that I'm going to use most of the time. So an example of orbifold with non-isolated singularities will be the Z2 small n orbifold, described by 3 complex planes, where the action, the orbifold action, is in units 1, 1 to n minus 2 of the Z2n action. Okay. So let me just use this example of this pictorial representation of the geometry. So there is now the conical orbifold still. There is a singularity at the top of the cone, is C2 mod Z2n singularity, and that's the one that creates in 5 dimensions, 5-dimensional SCFT. But then we are dealing with the sector where we have the codimension 4 singularity that extends all the way to the boundary, and it's associated with C2 mod Z2 plane. And again, we often refer to that as a flavor brane because it's non-compact itself. Okay? So again, at the cone, we are dealing with 5D SCFT, codimension 6 singularity, producing for a SUN resulting quantum field theory. And then there's codimension 4 singularity, which appears at taking Z1 and Z2, 0, is associated with the SU2 flavor brane symmetry. Okay? So the way we can see now resulting field theory is 5-dimensional SUN superconformal field theory, but it can be viewed out as a defect, 5-dimensional defect within 7-dimensional SU2 super Young-Mills theory. So taking this non-compact extra dimensions, right, will produce for us higher dimensional dynamic quantum field theory, and the 5-dimensional one is now a defect in it. So this is, as a field theory construction, a nested type of quantum field theory. So now I have to, within this context, construct nested sim TFT. Okay. But before I do that, okay, let me point out that the structure of this non-isolated singularities produce for us actually the geometric origin where we ended up with one-form symmetries, actually in general higher form symmetries. Also, we are dealing with zero-form flavor symmetries, one-form symmetries, and they happen to be intertwined that led actually to the quantum field theory with the two-group structure itself. Okay? And the way we studied just the elements of this symmetry, higher form symmetries, we never resolved geometry. What we did is actually we constructed symmetry defects now associated with the structure, the algebraic topology, where we were just cutting and gluing singular boundaries of this non-compact space. And that allowed us at the end to identify precisely the elements of higher symmetry structures there. And techniques, mathematical techniques involved actually Meyer-Vietoris sequences. Subsequently, in this program, we turned to observation how to completely construct for this type of non-isolated singulars, how to completely construct nested sim TFT. And again, as I'm saying, this would be now joined 7D super Young-Mills with the 5D defects, which is 5D superconformal field theory. Okay, and within these explicit constructions of nested CMTFT, of course, we reproduce the old results. But this approach turned out to be more general because we can now study any topological operators, not just the specific ones that we are focusing in. And we can study through boundary conditions and directly how such topological operators behave when pushed from the symmetry bulk theory to the edge boundary sim TFT. Okay, those are words, but let me just construct it just to highlight a few steps how this construction of nested sim TFT happens in this context. Okay, so let me remind you, right? We were dealing with this codimension 4 flavor brane singularity. So in these extra dimensions, it was 7D super Young-Mills, right? Flavor. One dimension we can just compactify, like a circle in this codimension 4, right? Extended flavor brane. So dealing basically with 6D flavor quantum field theory. Okay? And then on top of it...
Is that an assumption or is it expected that you always
Rewriting.
For specific questions we are asking was clearly, this KK reduction did not, namely, this extra redundant circle did not give us, was not relevant for studying specific things, yeah. But if there are more refined other questions, maybe one has to be more careful, right? But demonstrate prototypes for you that work and how they work. And so there's codimension 6 singularity and 5 singularity is now viewed as the end of the 6D super Young-Mills.
It's because it's non-compact, it makes sense, right? So that's the essential thing.
No, not necessarily.
No, so the KK here does a lot of lifting.
Yeah.
It tells you that you really are just rewriting. So that theory is intrinsically still 7D in a way, but you're presenting it with respect to a 6D spacetime. And the only reason to do it is then later on things are an adjacent dimension and it boils down to a more uniform framework rather than having to drag along co-dimensions of every specific example at every point.
It's a bit of bookkeeping.
Exactly.
I see.
It's a bit of bookkeeping. It's not that crucial for this thing, okay? But it's not the first time this question was asked. Yeah. And so this SCFT, 5D SCFT is now at the edge, okay? Now, to construct nested sim TFT, we have to construct the symmetry theory that is normal geometry, both to this flavor brane and to SCFT. Okay, so this is the normal geometry. So this implies that we have to do specific reduction of the topological 11-dimensional supergravity theory. Okay, down to this normal geometry and produce an extra dimension now over super Young-Mills and extra. So this is image over that one. So this is 7-dimensional sim TFT that lives above super Young-Mills and extra dimension on the boundary that is associated directly with this sim TFT of 5D SCFT. But they are together. They are intertwined. Okay? So again, result is that the bulk flavor brane produces this bulk SIM-TFT 7D, and the edge SIM-TFT or boundary SIM-T is associated with 5D superconformal theory. All right. So directly now, if we want to focus on one-form symmetry backgrounds, for this first super Young-Mills, namely the flavor theory, quantum field theory, this one-form field, one-form symmetry is actually sourced by 2 cycles. Because it's torsional, there are 2 cycles. So for the super Young-Mills SIM-TFT, it's associated B2s that respect Z2 symmetry. And for the edge one that sits above superconformal field theory, we are dealing with B2 co-cycles that sit in Z2n. Okay. Now, these 2 co-cycles that we obtain from reduction of original C3 of 11-dimensional supergravity, blah, 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 okay? They are not independent because the bulk, one form, 2 cycles, and the boundary 2 cycles, okay, impose boundary conditions on the bulk one. And that means we are dealing with n boundary conditions. So among all 2B2 independent Z2n, we are dealing only with a subset of them due to this boundary condition. So the actually naive one-form symmetry, which would naively be Z2n, it's not that. These boundary conditions in this nested field theory on B2s really produce now, for us now, only Zn of independent one-form background fields in this H SymTFT, right? And so there is one lesson with this very physical, right, results, is that the symmetry structure of this corner mode so the symmetry structure of this 6D CMTFT, right, are actually not independent because they are constrained modulo boundary conditions of this bulk CMTFT, all right? And there's boundary conditions. Another lesson is that actually this boundary condition intertwining of one-form symmetry that extends, that is extending by this bulk flavor brane one-form symmetry. This interplay is typically a hallmark also of having a bigger structure, a two-group structure. I could go into technical answers how this comes about, but I'll skip it. It's the old works, okay? All right, now how am I doing? Not so good. Yeah, I took my time, I'm sorry, but I also took this time to be a little bit more pedagogical and a little bit giving an overview. 20 minutes, yeah, but because this is basically now the core of the work, okay? Because I gave you this perspective on the identifying the nested SymTFT and also identifying the symmetry group, say, of the one-form symmetry in this particular context. But we want more. We want more refined data of SymTFT, including, in principle, this nested TFT. Okay? And for that, in particular, the SymTFT effective theory will include for us topological terms with specific coefficients. And it's this anomaly coefficients that we should be able to quantitatively determine. So this is the next refined level of studying features of effective SymTFT is really anomaly coefficients. And so is this anomaly coefficients that we want to calculate in the singular geometry. So this is the actual aim. So let us recall that what we are basically dealing with, we put M theory in lower dimensions, right? 1, small d dimensional field theory times non-compact space that is cone over specific boundary. And so if we excise the singularity, the physical co-dimension 6 singularity at the tip of the cone, the space can be viewed effectively as a boundary, the interval, and this resulting dimension of quantum field theory. So the SymTFT can be viewed as extension of regional field theory to this extra interval that comes by the compactification on the boundary. So I'm just going to use this view by now starting the discussion of anomaly couplings in SymTFT. So to address this anomaly couplings in SymTFT, we first start with this 11-dimensional theory, supergravity theory, and focus on supergravity topological terms, which are well known. They involve the three-form potential, and also a number of geometric terms, the so-called Pontryagin classes. And this is the topological part of 11-dimensional supergravity. Now, to write this supergravity action, topological part, in gauge well-defined way, so globally well-defined way, is to extend it to the 12-dimensional action, and now everything is expressed in terms of field strength of three-form potential. And this is the well-known 12-dimensional Chern-Simons action of 11-dimensional supergravity. Now, what we are after is anomaly terms in our SIM-TFT, which would be taking this action, leaving field theory, a D plus one dimensional field theory part, and an interval intact, and the rest would be reducing it on another space, which is 6-dimensional. Okay. Now, the only thing that we have to make clear is that this x prime need not be the original x as long as the boundaries are the same. Okay? So the boundaries matter of this guy. That's why resolution worked, okay? Because it could be another space, and yet physics comes back, right? So this is the logic, and we are after precisely identifying key anomaly terms, all right, of properly reduced Chern-Simons action of 12 dimensions. Okay. So let's see first how the SIM-TFT anomaly terms appear in the case of isolated singularities. Yes?
Chern-Simons function doesn't change, right, when you take different bulk for the same value. But is it the exact value doesn't change in 1112D, or it's mod something that doesn't change? Is it the exact value that stays invariant?
Mod 1.
Mod 1.
Oh, yeah. But that's, yeah, doesn't matter exactly. So in any case, what we want to do is a case of isolated singularity, and that is just regular SIM-TFT, and include one. So I want to focus on one-form symmetries, which are sourced by two cycles, P2 background fields, and we expand them out of 4-form field strength of 11-dimensional supergravity over the backgrounds that sit in the internal space. F2 sit in internal space in specific cohomology, okay, and result now in the anomaly of our SIM-TFT, so action associated with the anomaly of our SIM-TFT. So there is the standard quadratic type B, wedge F type terms that appear in this reduction in the anomaly action of SIM-TFT. And were studied, and they are geometric coefficients, which I already wrote in specific way. And we want to focus now on examples of one-form self-anomaly and mixed gravitational anomaly that involve this Pontryagin class. And then coefficients beta and gamma are coefficients that we are after. And so this is the ultimate thing for the specific type of anomalies. More. So how do we get to it? Right. So for that purpose, to determine this alpha, beta, and gamma coefficients, okay, let me first focus on calculation of coefficients that are sum of beta and gamma. It turned out to be the case. Okay. And for that, we can employ the APS Singer index, which is a Dirac operator index on this extra dimensional space that is coupled to a line bundle with first term class associated with this background field F2. Okay. So this index is built out of two pieces. So this is an integer. That's why it's index. It's built out of the bulk piece. When we integrate over the bulk over this extra dimensional space, and the expansion offers term classes and the Pontryagin.
Is your operator on what bundle? I mean, that's a line bundle. You need
Yes,
another
it's
bundle.
line bundle specified by this background F2 field. Okay.
Should give you another rank 2 bundle too, right? Because you're writing the wrong operator.
Oh, there's standard Fermi to the system. Then it's just with a bundle.
Twisted by this line
Twisted
bundle.
by
I see.
Oh yeah, because in 4 dimensions it matters.
Yeah,
But here it doesn't.
when,
Yeah.
when a physicist hears Dirac operator, they think of spinors and spin bundles.
And this is,
This
yeah,
needs to be specified.
Yeah.
indeed. And the second part is the boundary part. Okay. And the boundary part, okay, this part turns out to be precisely alpha. Because if you look back, this plus this is precisely the bulk. First term class and Pontryagin. So the bulk part of this index is precisely what we call alpha.
I see. F2 was your curvature, right?
Exactly.
Okay.
Yeah, F2 is the expansion is exactly in terms of F2,
Oh, yeah.
right? This is the expansion, and B2 is now sourcing the one form. Those are one form fields. Okay, and so the boundary involves now 2 terms. One is the dimension of the kernel, but because of the curvature of this boundary, this is automatically 0. But the other boundary piece is really the spectral invariant, eta spectral invariant of the Dirac operator on the boundary. So it's the boundary, it's spectrum of the Dirac of the boundary, and those are the so-called Eta invariances. Okay, so we are dealing with the introduction of something that is integer and is equal to alpha minus the spectral invariant eta on the boundary. Now, what is key for us, this boundary has to be the same as the boundary of our original non-compact space. And so we get, in principle, the answer that the sum of these coefficients, beta and gamma, modulo integers, is equal to 1/2 of Eta invariance. Okay. And
You don't know what is the eta explicitly, right? You're just using the fact that it's integer. Oh, you
yeah, we are really exploring. We don't have to do it from scratch. It's mathematicians. Yeah. Yeah. So, thanks to work of mathematicians, for example, of the case of isolated orbifold singularities, right? So this is parameterized by Z and orbifold with these weights in each plane, PQR, in such a way that we don't have any, we have only isolated singularities. This 1/2 of Eta invariance is really explicitly calculated with the natural phase factor of 2 pi I over n, summing over all the sectors except to untwisted one. Okay, so that was calculated. So in principle, for all those orbifolds, okay, and the charge of the line bundle is 1 in this case. Okay. So it turns out that actually the old-fashioned work was really dealing with X prime, resolve it using intersection theory, do the bulk calculation, and getting the answer, which we want, okay? And that was the work. And of course, we had to recheck that carefully also ourselves in our calculations, okay? Oops. The new thing is, do not resolve anything. calculate this sum of beta and alpha directly from this eta invariance and get the answer. And of course, with careful matching, we see that they agree, right? So that was not doing that directly, doing this, and we see that with the harder work, where we lose also all the geometry because all this is resolved, right? Now we have direct singular space calculations, okay? So this, my prototype like that, will give me alpha to be this. And it's true for all the, you calculate it for all of them, PQR. And then you can also separate, refine this alpha by getting beta and gamma separately, because all I calculated is sum of beta and gamma, okay? So one has to refine that, but by actually using the rescaling by charge Q, that is co-prime with N, okay?
What was the other approach that you said it agrees with your result? It was doing it without,
resolution.
with resolution.
Only doing resolution, intersection theory in the bulk, historic resolution, and doing intersection theory and getting results. Basically, what the other calculation is resolving things and calculating this. Calculating this. Basically, that's what he does. In the smooth space. In the smooth space, right? And because we know the answer would be okay, can be anyone as long as the boundary is the same, we are fine. That's why this is the great success of resolution theory. But you lose you have to go through lots of steps, right, to do that properly. And Max can tell you all about it because he labored painfully over all this.
What is the context for that? Is it M theory too?
Yes, a prototype I chose was M theory.
Yes, but the old story.
When people have looked at it all,
You see, 21 earlier. You see that? This is old story. 2025, 24, 25 is new story.
And intersection theory here means intersection theory on what exactly?
It's the,
so this is the torque space, so you can do torque
Yeah,
resolution.
yeah. Okay? All right, I'm running out of time, right? I'm giving you something, you have 5 minutes, not much. You're very generous because it's the stuff together with Max. I'm saying that, or he's just kind. In any case, so we can rescale those generators by Q, but that means our beta and gamma would rescale accordingly with the cube and Q, okay? And so we can calculate alpha by choosing the charge Q to be arbitrary, but we have general result for Eta invariants for line bundles with any choice of charge Q. And so in this case, there actually turns out to be one preferred Q, which matches precisely on the way the resolution works. And that has to do with taking Z3 as being special direction, right? The so-called Kawasaki divisors and so on. Anyway, let me not go into technicalities, but Max can tell you all the technical parts. And the point is, by doing that, we can actually separate, all right? Now refine anomalies into beta and gamma in terms of alphas. And that's an example. We'll write Eta invariants for 2Q and Q, and then solve it and get universal beta and gamma out. And that allowed us to get all the separated anomalies, beta and gamma, and that's chosen specifically for the so-called Kawasaki preferred generators, right? And get all the refined anomalies, for example, of all, this is one parameter classes, but this is actually generalized to 2 parameter classes of isolate singularities. So it's covered, orbifolds are covered with isolate singularities, okay? Now, last part is punchline. And that's something that kept us, how long? At least 6 months, right? From going ahead, which is studying carefully non-isolated singularities and trying to deal. This is, again, our prototype with this flavor brain, super young Mills, and super conformal field theory on the edge. And we are dealing now with anomaly coefficients that we want to calculate for B2 cube and mixed one in the case of this. And now you see what you see is now the boundary has singularities that have to do with flavor brains extending. And that wasn't clear how to properly address this with Eta invariances, okay? Nevertheless, by carefully matching results also for non-isolated singularities, this prototype happened to be studied directly in field theory by Guko et al. Okay. Also, somehow some special limit was found by those people because they primarily focused on isolated singularity, but they did have this as some special limit. And these two things work there. Okay. And now, Eta invariance should also produce for us alpha here. And it's Eta invariance calculated for this particular orbifold or this particular boundary of the orbifold.
The geometry of S5 on gamma, does it play any role? Like, does it matter what geometric structure, or do you care, or do you know what is the geometry on S5 on gamma? Is there?
I guess in this case it's Calabi-Yau.
Yeah, that's what I was wondering. Does it? Because when you go from like cone picture to the product picture, the geometry of the product thing is not the geometry of the cone thing, but the link stays the same.
Yes.
Right. Like if you had a Calabi-Yau threefold, which was a 5 manifold times that interval or R, whereas a Calabi-Yau threefold, which was cone over a 5 manifold, the geometry of those 5 manifolds would be different. But you take the same thing in both cases and it seems to work.
Sensitive.
And S5 is the very special thing that has that property, which is both compact and Sasaki Einstein. I was just wondering.
It's hard to see how this is encoded in the Eta invariance, right? And by the way, it was taken from mathematicians' calculation, right? So let me specify. In this case, what is happening is this Eta invariance is calculated for this non-isolated singularity case has the summation only over the sectors that do not have extended singularity. K is not equal to n. This is the actual calculation, formal calculation of Eta invariance. Okay? And it turns out to be associated with the line bundle whose charge in this case is -2. And once you work this out, you see that all those things match. Okay. So is the singular part on the boundary that we remove in this calculation, okay? That I'm not saying that we don't understand that. This is math result.
So the difficulty was that you didn't know you shouldn't count K equals to n?
No, is this. We had to find a proper line bundle that supports that. Okay, and then of course we constantly match to resolve guys to make the precise matching and identify this line bundle associated also with the Kawasaki generators in the resolve geometry. Anyway, but there is a first principle determination of that for us now.
But this is what you said is like a divisor computation, is it?
Resolve one?
No. Previously you mentioned there is a divisor computation.
Oh, yeah. See, you sum over all the sectors, right?
Yeah.
Because those are, you see, this is the natural, right, phase of Z and orbifold.
Yes.
Okay? And then you have to calculate over all the sectors. K equal 1 to K equal, in this case is n is too small to n, because this is the case. Yeah, n is to n, and then you do all the sectors except the sector that does not involve the codimension 4 flavor brain in it. Okay, but this is the actual mathematics calculation. Okay, in its general. We always, in eta, in calculation of eta invariances, one always excludes this sector. And it's general calculation actually by mathematicians. Okay? And so we of course can now go and generalize that, n is the n, and any associated examples with non-isolated singularities, and calculate this eta invariances for line bundles with any charge q, again general formulae, and that allows us then in principle to get separate beta and gamma saying results for capital Q and 2q, and that will give us the general results. And so we have all the eta invariants also for examples with non-isolated singularities, and refining it further with these calculations, okay? So this is basically the solid calculation of the results, and of course checked against other result examples, right? But this is true also for calculations of non-cycling, non-abelian examples, the n cross the m cases. There are some results here, so on, right? So this is really a solid calculation. Okay, I don't have really, because this is just as a side thing, because there is the flavor brain that are non-extended, right? Associated with non-isolated singularities also produce mixed flavor anomalies that we could also identify, and in this case we did it directly with amino action and reducing it, and obtain also results for this. This is another side thing, okay? Maybe I'm distracting it from the main lesson, that is eta invariance for one form symmetry that I focused on, that governs the anomaly coefficients there.
You're writing like Chern-Simons function with respect to other structure groups, is that how you get it?
You mean those would be the flavor groups depending how many sectors we have? For Z to N, we had just one sector. It was SU2, I think, right? But now in general, you complete. So it's all, I give you prototype, then you get the whole calculation at the end, build up from prototype on, right? So let me conclude, since I think I at least conveyed the key points, or the key technical results, in particular the most recent one on eta invariance. And let me just say a few things that are clearly useful directions to look at. And we have now refined data on anomalies, at least for one form example that I was focusing on in this, both isolated and non-isolated, namely nested examples. And so this really detailed data that quantifies the nature of anomalies, we may want to confront that by using these non-compact examples and gluing them together into compact ones. There we know that anything that was anomalous originally has to be broken, because in compact cases, it's either broken or caged. But we already had it there, so it has to be broken. So there could be some more refined studies of gluing processes and the role of this anomalous, right? How it may further constrain features of the compact geometry. And well, this would be interesting. Maybe you have more to say, Max, right? Examples of non-geometric backgrounds like frozen singularities, at least from string theory, not M theory. Anyway, applications to terminal singularities and after more detailed features, right? Going beyond, like we managed to do that for non-isolated singularities. And yeah, well, this is already, I showed you some examples of non-abelian examples. non-supersymmetric constructions. Some of the examples already also in this paper, this whole program that Max, Jonathan, and others pursued. And I think one can really cover technical aspects in greater details, thanks also to the work of mathematicians. Thank you.
Thank you, Mirjam.
Okay, thanks.
We have questions.
So, is there a good example of this away from M theory? If I'm doing string theory instead, is there anything about this that goes wrong or that I should be careful about?
Well, we have examples, right, of string theory also on Calabi-Yaus, right? It depends how low you go in dimensions. Higher dimension examples are probably rather straightforward, and they're also analyzed in the paper in glorious
Well,
details,
to be a
right?
bit more concrete, so in M theory everything is geometry, but if I go down to the string theory, then I can have all sorts of weird effects with big fields and
Yeah, they need to change
singularities and
completely.
obstructions.
That changes completely. I think what Mirjam meant is that you can do the same. If you have a purely geometric background, you can do the same computation. But then often the question is, what are you computing? And so, for example, I guess the example that's closest to this case here would be to just consider type 2A in the same geometry.
Yeah.
And there it's not reasonable to, the Eta Invariants don't seem to compute things that's intrinsic to the 4D theory. Rather, it's more to the 5DKK theory. So there's that.
I see, so in a sense this is still remembering the M theory origin.
Yeah, for that particular example. But other examples, it does compute reasonably. So it's, yeah.
But on the other hand, there's the other related, sort of a little bit reverse story. Okay, as you were telling me about frozen singularity, that we want to understand directly in M theory. And yet, type 2 string theory is more powerful because of K theory. So we have more powerful results there directly in K theory, and yet hoping if KK, if you go up in one dimension higher, if KK direction doesn't introduce any new features, then type 2 result will be good enough in M theory. So you were doing here now the related but reverse story. Here we have M theory under complete control, at least, right? Hopefully, I'm not eating my words for the future, okay? But then, yeah, please.
So can I think of these Eta invariants as being anomalous phases of like degrees of freedom that propagate on the link of the singularity?
So degrees of freedom
Like
sitting on, yeah.
Yeah, so for instance, if I have like a D-brane, right? Like at an orientifold, like for instance, if I want to compute like the D-brane charge of an orientifold, right, in type 2, then Tachikawa and collaborators showed that the fractional charges of certain orientifolds can be computed by the fact that the magnetic dual D-brane propagating on the link of the orientifold singularity is fractional, right? So there's a non-zero Eta invariant associated to the world volume fermions that gives rise to this fractional charge of the D-brane at the orientifold singularity. So I'm wondering if the fractional couplings that you get here arising from the Eta invariants that you get can be also thought of as Eta invariants associated to like world volume degrees of freedom with the magnetic dual.
I haven't thought about it, but maybe Max did.
This paper doesn't know.
Yeah.
I asked because
Yeah, it's a very interesting question. Worth rethink, right? But definitely I don't have much to say. This paper hasn't thought about it.
No, I asked because that's something that we're thinking about currently, so I was
Yes.
curious if, yeah.
Might be interesting, yeah, to see that, yeah. Thank you. Okay. Thank you very much. Yeah.
I think we have no more questions. Let's thank Mirjam again.